Thank you for joining us today and welcome to everybody. My name is Emily Giles and I am the lead specialist here on the Science, Knowledge and Innovation team at WWF-Canada. I'm joining today from the traditional territory of the Algonquin Anishinaabe, located just outside of Ottawa, Ontario, and I help to lead our carbon monitoring work here at WWF. So thanks again for joining. This is the third session in our four-part series. Today we're going to be talking about vegetation and trees. So we'll be branching out to cover vegetation. Okay, so for those of you who have joined us to date, I think you probably know the drill so far. We'll follow much of the same protocol as we have in previous times. So we will share this session and we will share it with participants following the seminar. And we're also going to share the recording in the WWF Learning Library. And Catherine is going to post the link for that there in the chat so that everyone can access the Learning Library. We've also got, thanks to, again, Catherine Paquette, we've got translation available today for English and French. So if you have questions or comments in French, please don't hesitate to send those in and Catherine can help translate for you and for us. If you have any questions, please go ahead and enter those into the Q&A section, which is just located in the menu. You can type the questions in there. We'll try our best to answer them as the webinar proceeds, but we'll also hold a dedicated time at the end of the webinar to answer any questions that you have. So feel free to either enter them there or hold them to the end if you prefer. If you have any technical issues or questions, either during or after the webinar, please do email us there at science@wwfcanada.org. So today, in terms of our agenda, we'll do some quick introductions, and we'll follow that with a brief overview of workshop 2 for folks who maybe missed that workshop or just want a quick refresher. And then we're going to get into the detail on how you actually go about surveying trees in the field, as well as surveying and sampling vegetation. And then we'll do just a quick walkthrough of some of the select resources that we have to help demonstrate that before getting into the question and answer period. So for this webinar, we're hoping you'll come out at the end knowing how to actually survey trees in order to estimate soil carbon, knowing how to set up plots to estimate carbon in vegetation, so non-tree vegetation. We'll go over some of the equipment that you'll need to estimate carbon in both trees and vegetation. And finally, we'll go over how to go from individual estimates to plot or study area estimates. So hopefully by the end, you will know how to do all of those things. So before we get started, we'll just quickly introduce our team. And we also would love to hear from those of you who are joining us on the call today. So if you don't mind just taking a moment while our team is introducing themselves to put your name and affiliation and role, as well as your location. If you don't mind just entering that into the chat, and then we'll have a good sense of who is joining us today. So to kick things off, I will pass it over to Catherine to start our introduction.
Emily, hi everyone, I'm Catherine Paquette. I'm a specialist of freshwater ecosystems at WWF. And today I'm joining the webinar, as Emily stated, to help with translation as needed. So if anybody needs a little bit of clarification and wants to ask a question in French, I'm happy to translate it so everybody can understand, and vice versa. Donc, bonjour tout le monde, mon nom c'est Catherine Paquette. Je suis spécialiste des écosystèmes d'eau douce ici à WWF-Canada. Et aujourd'hui, je me joins au webinaire pour aider un petit peu en traduction. Donc, si vous avez des questions que vous voulez poser en français, s'il vous plaît, n'hésitez pas, ça me fera plaisir de le traduire pour l'équipe et vice-versa. Donc, s'il y a quelque chose que vous ne comprenez pas ou si vous voulez un petit peu plus de clarification, s'il vous plaît, laissez-moi savoir et ça me fera plaisir de traduire. Merci. I'll pass it over to Claire.
Thanks, Catherine. Hi, everyone. I'm Claire Wark. I'm a specialist on WWF Canada's Science, Knowledge and Innovation team. I live and work in Collingwood, Ontario, along Georgian Bay, which falls within the territory of the Anishinaabe Nation, along with the people of the Three Fires, the Odawa, and the Potawatomi Nations. This land has been traditionally managed by the collective Saugeen Ojibwe Nation. And while I'm in my role at WWF Canada, I spend a lot of my time connecting with communities about carbon, leading carbon training and fieldwork initiatives, as well as supporting our carbon community of practice calls, which happen every quarter. So I will pass it over to Cal.
Thanks, Claire. Hi, everyone. My name is Cal Doherty, but I go by Cal. I'm an associate specialist on the Science, Knowledge, and Innovation team at WWF Canada. My work stems from experiences working on ecosystem carbon cycling throughout all of Canada, focusing on providing tools and information to build capacity of individuals who are also interested in this kind of work. But yeah, I'm excited to be here today to discuss some carbon measurement in vegetation and trees. And with that being said, I'll pass it on to Marianne.
Hi, good morning. My name's Marianne. Oops, sorry, camera's off. My name is Marianne Fish. I'm the senior specialist for coastal ecosystems on the Science, Knowledge, and Innovation team. I live and work on the traditional territories of the West Saanich peoples on Vancouver Island and the Saanich Peninsula. And in that role, I co-lead our Blue Carbon program and work on projects throughout British Columbia, looking at stewardship of coastal ecosystems. Thank you.
Thanks. And before we continue, I did notice that Jane Valesky had her hand up, so I just wanted to make sure that we're not missing a comment there. Yes, Jane, you can go ahead. Maybe it's an issue with a mistake. Okay, yeah, no problem. Thanks for clarifying. Okay, on that note, I'll pass it over to Claire.
Hey, perfect. So first, we're going to do a bit of a review from our previous workshop, which was on soils and sediments. We're not going to spend too much time on this piece. Really, I wanted to highlight some key areas where there's overlap between so our last workshop and then this workshop on vegetation and trees. And so in that workshop, we covered what soil carbon is, as well as what sediment carbon is and the difference between those two, as well as how to measure carbon stocks in 5 steps. And so while the fieldwork involved in carbon measurement varies depending on the carbon pool that you're looking at, the core steps that we've highlighted here really remain the same for the most part. So I'm going to review the steps now, and then also go into a bit more detail about the first 3 in the coming slides and talk about how there might be some differences for the content today. So in step 1, you define your study area of interest and its boundaries. Following this, you need to determine how many samples you want to take, of course. And then after that, you need to determine where you're going to be taking your samples. Following this, in step 4, you actually head out into the field to collect your samples and other data. And so in our previous workshop, this was talking about doing soil pits as well as soil cores. So you can see in the photos shown here on the upper photo, we've got a soil pit showing the different horizons in the soil very clearly. And then on the bottom photo, there's an example of a soil core that you might take in a more wetland type environment. And then finally, step 5 would be heading back to the lab where you would do analysis on all of your soil samples, or alternatively sending them over to a lab where they would be doing the analysis for you on your samples. So next slide, please. Like I said, for our review, I'm going to expand on the first 3 steps a bit further, as there's quite a bit of overlap between the protocols for soils, trees, and vegetation. So when defining your study area in step 1, you'll want to consider your project goals, as well as any other goals across maybe departments or different teams, or maybe even within your community, there's specific goals that you're trying to address. And there might be also areas there that are flagged that are really important either to include in your study area or possibly exclude. So it's important to really know those from the start. Alternatively, you might have a predefined project boundary, either based on an existing project that you're working on, or maybe a funding agreement that you've agreed to. So once you've identified your project or your study area boundary, you can then map it out using a software like Google Earth Engine or ArcGIS. Once you've got that, you can then move on to step 2, where you're ready to determine how many samples you would like to take. And remember that by sampling an ecosystem, you're actually selecting a small portion of the total area to then approximate the carbon value of the larger area. And so that's why it's so important that your plots are representative of the entire study area. You're not cherry picking, certain areas for your plots and your samples that when you then scale up your estimates of carbon, you are left with something that's very biased in one direction or the other. The number of your plots and samples will depend on the following 3 things. So the size of your study area, your project goals, and your budget. So a larger study area, it doesn't necessarily equal more samples and more plots, but oftentimes the larger your study area, the more opportunity there is for variation across the landscape. So the higher levels of variation will require more samples in order to truly capture that variation. In terms of project goals, we really want you to think about the level of accuracy that is acceptable to still meet your goals. So if your goal is simply doing an initial field season, getting a sense of the carbon stock estimate, and you're just going to use it internally for your team, maybe to begin some discussions around land use planning, you can have a bit more room for error. On the other side of things, if you're intending to report back to funders or set up a carbon credit or offset program, you'll need a higher degree of accuracy. And because of that, you'll need more samples. And then that brings us to budget, which will likely be the main factor when determining how many samples you'll need to collect. When planning your budget, it's really important to consider staff time, as well as equipment costs, transportation, shipping, lab fees, and those last 2, shipping and lab fees, are specific to soil samples and sediment samples that are being sent to a lab for analysis. Working within your constraints of a budget will also mean that you need to prioritize certain areas. So this could mean if you've got a really large study area, stratifying or identifying these sub areas that are unique. They've got unique features or aspects that you want to capture when you're sampling. And so we'll talk a bit more about that on the next slide, which we can go to now. Perfect. So on step 3, this is where we determine where you're going to take your samples by deciding which sampling strategy is best for you. So there's 4 main sampling strategies you can use, and each has its own pros and cons depending on your goals, your study area, as well as your budget. For random sampling, you set up a grid or a transect with numbered intercepts, and then use a program to randomly select intercepts where you'll set up your plots. And this is really useful when, say, your study area is more uniform, or in cases where you may not know that much about your study area. Maybe you know a lot about specific zones, but you don't have a good overall knowledge of the variation exists. So this would be a really good strategy to use then. And it's also recommended as the default sampling strategy. So if you're not entirely sure which one would be best, take a look at using random sampling. For systematic sampling, you evenly distribute your samples across the study area. So this is good for smaller study areas that are typically more uniform. And in order to use this strategy effectively, you must understand the variability across the entire study area. That's really important for this one. There's also stratified random sampling, which is what I mentioned on the last slide. So this is where you first divide your study area into smaller units based on landscape features or other characteristics. And then from those smaller units, you randomly select plots and sampling locations. So this is really good for a larger study area where there's known variability, and you want to make sure that that variability is being captured when you're doing your sampling or your surveying. And last but not least, there's convenience. So convenience is really, it's the most cost effective in that you simply select plots based on what is easiest to access for your field crew. What's the easiest points for them to get to set up these plots and collect samples. So we don't have that one shown in the images on the right, but the other three are shown there just to provide a bit of a visual aid for you. Okay, next slide. So after determining your sampling strategy and plot locations, you're ready to head out into the field and collect your samples and site data. And this is where the steps for trees and vegetation diverge from what we discussed during our last workshop on soils and sediments. So we have 4 guides that you can refer to for the exact protocols when sampling soils, trees, and vegetation. These can be found online in that carbon measurement learning library, which I believe was already entered into the chat. So you can just scroll up a bit to find them. And once you've followed your field protocols, you'll take your soils and sediments back to the lab for analysis to estimate your carbon stock. And we'll discuss how this step differs for trees and vegetation in the coming slides. Okay, next slide. So before we jump into the new content on trees and vegetation, we just wanted to learn a bit more about who's joining us today. And so I'm going to launch a quick poll. Feel free to take part in it if you like. Otherwise, you can just take a quick little break or maybe check out who's joining us in the chat. Cool. There we go. And so we'll just give some time for folks to look at the questions. You can answer just one, you can answer all 3 if you like. One of them is a bit of a quiz question there at the end, asking about what the recommended default sampling strategy is. And so far, it's looking like a pretty even split between people who have completed a tree survey before versus those who haven't. But I'll leave it open for a little bit longer. Okay. So now you guys should be able to see the results on your end. So slightly more people joining today who haven't completed a tree survey before, so that's great. But also good to know there's lots of folks with experience on the line. And it looks like in terms of the interest in different carbon pools, it's strongly swayed towards trees. And for the quiz question, so the right answer was random sampling strategy. So that one where if you don't know a lot about the landscape that you're going to be sampling on or surveying, random is typically the best default sampling strategy for you to choose. Okay. So we can move on to the next slide, Emily. So for the next portion of the workshop, we're going to discuss how you can survey trees to estimate carbon stocks in an area. Okay, so let's first define what we mean by surveying trees. So in this context, we're referring to the identification of a subset of trees in an area, and then the collection of measurements from those trees in order to assess specific features. So for us, that's going to be carbon, but you might also find that people do tree surveys for other reasons. So the methods that we will be covering for carbon estimation are non-destructive. So that means that the measurements that we take don't damage the tree in any sort of way. But there is another method I wanted to highlight just here at the beginning, that's destructive measurement method. And so this can be used for carbon measurement, and it involves felling the tree, separating it into parts and weighing each part. And then following this, a subset of the tree's parts are taken to a lab for drying and weighing to determine the accurate estimate of biomass, which is then applied to the entire tree. So you can kind of see this process in the photos on the right from start to finish. And there are some benefits to this method. The main one being accuracy. It's very accurate because, of course, you're actually taking apart the entire tree and systematically weighing it as well as drying certain pieces. But there's also a number of cons. And so this includes that it's very time consuming. It takes quite a bit of time and a larger crew to complete. It also requires more specialized skills for you to complete it. It's not as easy as, you know, picking up some tools and heading out and being able to do it all on day one. And there's also some safety risks that go along with the field work because you're felling the trees. Another thing to flag here is that if your project goals are tied to conservation of carbon or conservation of a specific area, then it might also be a bit contradictory to that goal if you end up, you know, doing this destructive method. So I just wanted to highlight it because some of you may have heard of it, some of you may have actually completed it before, but the reason that we're going to be focusing on non-destructive methods are just because oftentimes it's more aligned with folks' project goals for the work that we're completing. Okay, next slide, please. Moving on to specifics for non-destructive tree surveys, this slide shows the equipment needed for the protocols that we'll be discussing. This list can be found in the full guide on measuring carbon in trees through our learning library. And I'll just flag a couple of these items. You definitely don't need to write them down or note them, but I just wanted to highlight here that the DBH tape, or diameter at breast height tape, is really highly recommended versus a regular measuring tape because it reduces that room for error when calculating the tree diameter. I know sometimes all you have is a regular measuring tape and you can use that, but it does introduce this element of human error when you're out in the field. And DBH tapes are quite easily accessible through online shops or in-person shops that you can order them from. The other thing I'll note is that the smartphone is really great in that it can do a lot of different tasks here. So it can be used in place of a GPS unit. It can be used for photos and documenting your site. It can be used in some cases for species identification. And then if you have a newer phone that has LiDAR, it can actually be used to measure tree height in some instances, which is quite cool. And then the last thing I'll note here is about the laser rangefinder, altimeter, and clinometer. So these are all tools that are used to help determine tree height. So if you're not familiar with those terms, that's what they're used for. And we'll talk about them in more detail later. Next slide. Okay. As we reviewed earlier when we were going over the past workshop, the sampling strategy you choose will depend on your study area and your project goals. So as a reminder, random sampling is a really good default method, especially in cases where you may not know about variation across the landscape. So once you've decided on your strategy, you can determine what type of plots you should set up. Plots fall within study sites, which are then parcels of land within your larger study area. So more plots will be required in larger sites with more variation. For trees specifically, there's a standard plot size of 400 meters square, and the plots can be circular, square, or rectangular. And we've included the appropriate dimensions here just for reference or suggested dimensions in the case of square and rectangular plots. And another thing to note that's really important is that if your plot is sloped in any way, this will also need to be accounted for by adjusting your plot size. This can be done by first measuring the slope as a percentage to a point on your plot radius, and then referring to the slope allowances table in the NFI guidelines. So the NFI guidelines are something that you'll find at the end of this presentation in our resources slide. And there they will actually tell you the required area for your plot. So it might be a bit bigger than 400 meters square, depending on the slope. Next slide, please. So you should also decide at this point if you want your plots to be single use or permanent. Permanent sample plots are used to monitor trees or vegetation over longer periods of time. And deciding on the placement of these plots is really important to ensure that variation is captured, as you typically won't be reselecting plot placement each year. Once you've set up a permanent plot, the hope is to keep it in that same spot for years and years to come. We have more detailed steps to help you set up permanent plots in our guide, but in brief, you will use your typical methods to document the boundary of the plot and then label the boundary using stakes, and the individual trees will be marked with metal tree tags. You'll then want to make sure that the access of the plot is well documented, especially if you are in a remote area. You want to make sure that future field crews know exactly how to reach the plot in an efficient manner so that they're not wasting time, wandering all around trying to figure out which road is best to access the plot that you've set up. Another option to consider when planning your plots is if an integrated plot design would be useful. So this involves setting up plots for multiple carbon pools within an overlapping area. And you can see there's a visual of this on the right. So you can see that there are plots for trees, soils, medium vegetation, as well as small vegetation, all within that integrated plot shown. And so this integrated plot could also function as a permanent plot if that's of interest to you, in which case any sort of destructive measurement, so say collecting small vegetation or collecting soil samples, that would all need to take place outside of the permanent plot in order to maintain its integrity into the future years. Okay, next slide. Once you have decided on the shape of your plot and whether it's going to be single use or permanent, you're ready to head out into the field and actually set it up. So to do so, you will use a laser rangefinder to mark the border of your plot. You can use a large flexible measuring tape to do this, but it depends on the plot. So if your plot has a lot of really dense vegetation on the forest floor, it might be more tricky to maneuver using a flexible measuring tape. And so a laser rangefinder might be easier to use. But once you've defined your plot boundary, then you can flag all of the trees over 2 meters tall along the border and then inside of your plot using flagging tape. And as you go along that border, any trees that are, they're almost in or they're almost out, you'll need to decide based on where the center point falls on the tree. So if you imagine the very center of the tree trunk or the tree stem, if that falls on the inside of your border, then it will be counted in your plot versus it falling outside of your border. And if it so happens that, say you've got a tree that forks, it forks right at the border line, you will look right below the fork, and again, right in the center of the trunk or the tree stem. And that will be the deciding factor, is if it falls in or out of your tree plot. Okay, so with your plot set up, you can then record the coordinates, date, plot ID, as well as the elevation on your data sheet. And yeah, you're ready to move on to the next step. So next slide, please. So with all trees over 2 meters flagged, you can now collect data for individual trees. You can start by creating a unique tree ID for each of your trees on your data sheet and then identifying the species. The species is needed to accurately estimate biomass because the allometric equations used that have been created with data for individual species. So for some biomass calculators that you'll find online, you may be able to just indicate if it's deciduous or coniferous, and then it will determine the amount of biomass based on an average of tree species that fall into those two categories. But in general, you'd like to be as specific as you can when identifying the trees. So if you're able to identify the exact species, then that's great, and you can include that on your data sheet. In order to identify species, there's a number of different tools you can reference. So you can look at dichotomous keys, or there's even a number of apps that you can use. And it's also really beneficial if there's a member of your field crew who is very knowledgeable on the common species in the study area. That's always great to have. And so if you're ever unsure of the species, you can always take a photo and then refer to it later on. Maybe, you know, the person who's very knowledgeable about species in the area couldn't come out that day. You can bring the photo back to them in the office and have them take a look at it. But it's always useful to have. On the bottom left here, you can see a visual representation of what a dichotomous key looks like. If you haven't used one before, I would suggest testing it out before you go out into the field, especially if you're on a bit of a time crunch, because it can take some getting used to if you're not familiar with the format. This isn't exactly how it will look like. It's a more visual representation. So oftentimes there aren't these visual cues for each of the branches, but instead there's written indicators where it guides you of where to go next until you've narrowed it all the way down to this species. And then on the right is just an example of one of the apps that you can use. So this is Seek by iNaturalist. And after using it in the field a little bit, it's sometimes very accurate, and then other times it doesn't get you down to that individual species level, but it does a good job of narrowing it down a little bit. So next slide, please. Once you've identified the species, you can then measure the tree height as well as the tree diameter. Tree height can be determined using a laser rangefinder, a phonometer, and then, like I said, some smartphones are also capable of determining tree height now. And this is done by taking multiple measurements at a distance from the tree, where you can see both the base of the tree as well as the very top of the crown. For a laser rangefinder, we've included the image on the right, and so that shows you exactly those three measurements that are needed to calculate the tree height. For diameter, you'll use that DBH tape, the diameter at breast height tape, at roughly 1.3 meters above ground. So you don't need to measure out on each and every tree 1.3 meters. Instead, it's really easy if you just find a reference point on your body that sits at around 1.3 meters, and then use that to determine where you'll be measuring. Once you've got the height and the diameter recorded, you can remove the flagging tape and move on to the next tree in your plot. And if it's the first time you're doing this, or maybe there's a couple people on your crew who are new to this, it will take a bit more time, but you'll get into a rhythm as you go. And so we recommend having a crew of maybe 3 or 4 people, because then you can break up your plot and, you know, give each person their own section to complete and work away on. Okay, next slide. When you've collected all of your measurements from the plots, then you're ready to move back into the office. So you can then go from measurements to carbon estimates, and this involves determining the biomass for each of the individual trees that you looked at. WWF-Canada has an Excel sheet available on our learning library where you can input your measurements for each of your trees, and then it will automatically calculate biomass and carbon. And you can see a visual of that at the bottom, but we'll also be doing a quick walkthrough at the end of this workshop on that worksheet, so you'll get to see it in action. And then there's also a couple other biomass calculators available from Natural Resources Canada, as well as NFI, or the National Forest Inventory. And both of these are also linked on our resources slide. So for both of those calculators that I just mentioned, the two by NRCan and NFI, they do not provide below ground biomass, but this can actually be determined by using the root to shoot ratio for either softwoods or hardwoods. And I've included the equations here for reference. You can see both of them there, where BGB just stands for below ground biomass. And so you can determine each of them there. And it's a bit different for softwoods and hardwoods. So for softwoods, you just multiply the above ground biomass by 0.222 to get the below ground biomass. And for hardwoods, there's a bit of an extra step where you take your above ground biomass to the power of 0.615 and then multiply it by 1.576. So once you've got that, you've got all of your biomass measurements, you can add them together to get the total biomass amount and then calculate carbon. And carbon can be really easily calculated by multiplying that biomass amount in kilograms by the carbon conversion factor. And the carbon conversion factor is 0.5. It's an approximation of the typical carbon content found in terrestrial vegetation, and it's really widely used across researchers and different organizations. It's not something that we defined here at WWF Canada. It's something that's used kind of across the board. Okay, next slide. Perfect. So in the next two slides, I've just broken down typical calculations for how you may want to scale up. So going from that individual tree level to the plot level, and then on to the site and study area level. These calculations are also all detailed in our guides. So if you want to come back to them, you want more details or information on them, you can refer to our written guides. And in the slides here, I've also included sample calculations. So you can see under each of the steps, there's a corresponding sample calculation to help you along. So to estimate the total and average carbon stock of your plot, you simply want to add together the carbon stock of all the individual trees and then divide by the size of your plot to get the average. So this is going to be 400 meters squared for trees because it's always 400 meters squared. And then in order to scale up to the average for the site, you can add together the average carbon for all of your plots and divide by the number of plots found within your site. Okay, next slide. So from here, you can determine the total carbon stock of your site by multiplying the average stock by the size of your site in meters. And then finally, moving on to scale up to the study area, you'll first add up the total carbon stocks for all of your sites and divide by the total size of all of your sites combined. And that will give you the average carbon stock for the study area. And then by multiplying this by the size of your study area, you'll obtain the total carbon stock estimate for your entire study area. So again, if this is a lot of information and you're taking it all in and you're thinking, oh my gosh, this is a lot to look at, that's totally okay. You can always refer back to these slides. You can look at our guide as well. And if you're going along after being out in the field and collecting your own measurements and you have questions, you can always connect with us over email, and we're happy to, review anything over email or even jump on a call with you to help you out. Okay, next slide. Right, so these are the resources that I mentioned specific to tree surveys. So at the end of the workshop, there'll also be one of these for vegetation, but these ones are specific to trees. So you can see there, the first point is that carbon measurement learning library on WWF Canada's website. And those are the specific resources that we've got for tree surveys. And then there's also some tools to help identify species, as well as the two biomass calculators I flagged earlier. And then there's also three main protocols that I've included here for conducting tree surveys. So there's the one at the very top, so compiled by WWF Canada, and then there is one by the province of BC, and then the one by the National Forest Inventory at the bottom. Okay, next slide, perfect. So before we move on to vegetation, we're just gonna do another quick poll. This one's only 2 questions, but if you're still with us, it'd be great to hear. Yeah. Okay. So just take a few moments, take a look at the poll if you're interested in answering one or both of the questions there. And now it is also a really good time, if you have any questions for the Q&A portion, you can start thinking about them, maybe enter them into the Q&A function at the bottom of your screen. That'd be really helpful for us later on. Okay, I think I'll end the poll. Share the results. So it looks like for most people, the major barrier for completing tree surveys as well as collecting information on vegetation is funding, which isn't too surprising. But then after that, it comes down to staff time and then staff expertise, which is quite interesting. And then for our quiz question about what is the carbon conversion factor, the correct answer, most of you got it right, was 0.5. And so you guys can remember that carbon conversion factor is used to determine the carbon content in terrestrial vegetation based on biomass. So very good, everyone. So now I'll hand things over to Cal.
Great, thank you, Claire. So I want to turn our attention to measuring carbon in non-treated vegetation of ecosystems. Don't mind going to the next slide, please? Thank you, Emily. So when we discuss vegetation, in the context of this webinar, we're going to be talking about plants that are under 2 meters in height. And this seems like an unusual way to kind of classify a plant community. Like there's certainly going to be non-tree vegetation that's over 2 meters. And I just want to clarify, and I'll get into a little bit shortly after, that this distinction is less about the specific plants, but it's more of a practical way to divide up plant groups that makes sampling of the plants a little more feasible. So smaller plant communities tend to be a little more dense, so the area that needs to be sampled can be a little bit smaller just to reduce that sampling effort and those costs. So that's why we're distinguishing plants into these different height classes. And in terms of vegetation under 2 meters, what we're typically talking about is understory vegetation. So those plants that grow under the forest canopy. We're also talking about early successional stages of a forest that's maybe been restored or recovering from a wildfire or a recent disturbance. And also the many non-tree vegetated ecosystems, tundras, prairies, shrublands, wetlands, and many more that exist. Next slide, please, Emily. So relative to the amount of carbon found in trees and soils, the carbon storage capacity of smaller vegetation is quite minimal. For example, the map on the right shows treed carbon in forest in bright colors, and that's on top of the vegetation, carbon in vegetation, and that's in that brown hue. So we can see by the legend that forests on average store about 10 to 100 times more carbon relative to vegetation, but there are differences spatially. For example, in South Central Canada, you can see in the prairies that there's a significant amount of vegetative carbon in that specific area. That's going to be primarily with those those agricultural and herbaceous plants that grow in the prairies there. And then also, if you look north of the boreal forest, you're going to get into that tundra ecosystem, which is that shrub dominant, that grassland and ground vegetation dominant ecosystem. But taken as a whole, if you're looking at Canada as a whole and the average carbon stock across Canada, the average carbon stock of vegetation is 0.04 kilograms per meter squared. And if you compare that to trees at 4.13 kilograms per meter squared and soils at 36.4, it kind of puts it into perspective. Where non-tree vegetation only comprises, less than 1% of the biomass carbon in all of Canada. Next slide, please. So given this, why measure vegetation? Well, vegetation is an important component of a healthy ecosystem, and it's increasingly being recognized in its role for carbon and nutrient cycling. So whether you and your team are interested in assessing, this whole ecosystem carbon pool for a specific area, or if your project is taking place in a non-treed area with predominantly, that vegetation cover below 2 meters, measuring vegetation in these systems is a vital component of this type of work. And lastly, I just want to mention that vegetation is also a crucial part of a growing ecosystem. So those ecosystems that are being planted in those early successional stages of either through a restoration project or recovering from a disturbance. So vegetation monitoring in those early days of a forest can also be quite useful in that case scenario as well. Next slide, please, Emily. So we can further categorize vegetation into 2 height classes. The first I'll discuss is medium vegetation, and these are plants between 0.5 and 2 meters in height. Sampling plots for this vegetation class vary from 16 meters squared to 100 meters squared, depending on the type of plant being surveyed. Short-statured trees, smaller trees under 2 meters, are typically sampled in a 100-meter plot, whereas shrubs and tall grasses typically grow quite dense in these dense patches. So those are typically measured in a 16-meter squared plot. And also, when we're referring to short-statured trees, these are just trees that either are young trees or maybe they have stunted growth from some sort of nutrient limitation, or if you get high and up a mountain, they could have oxygen limitations and that much. So the second plant category that I want to introduce is plants under 0.5 meters in heights, and those are sampled in small or microvegetation plots. And the plot size for this plant class is between 0.25 and 1 meter. And this typically includes your grasses, your flowering plants, your ferns, as well as your ground vegetation as well. Next slide, please, Emily. So I'm now going to dive into a little bit about how to actually measure carbon in vegetation. And for this, you're going to need some equipment. So here's an equipment list, but if you're interested in a more exhaustive list, please see the Carbon Measurement Learning Library, and you're going to find the Measuring Carbon in Non-Tree Vegetation Guide for a more complete list of the equipment needs for this type of work. Now, Claire already introduced some of the key equipment earlier, such as the DBH tape. But I just want to add another key piece of vegetation that's used for those smaller microplots specifically, and that's the use of a quadrat. And that is just a small square frame used for outlining a 1 by 1 meter or smaller plot boundary. And it's usually just a PVC pipe or any other material that you stick together just to make that square. You can carry around with it and just plop it on the ground and you have your plot layout, simply like that. Next slide, please, Emily. The first step when you're out in the field is to set up your plots. As Claire introduced previously, this can be accomplished for individual plots, and they could also be accomplished together using an integrated plot design. In either case, to set up a medium plot, you can use a laser rangefinder or a measuring tape and a compass to measure out your plot lengths and widths. Remember, this can be anywhere from 4 to 10 meters in length and width. And within this plot area, you're going to flag all the species between 0.5 and 2 meters in height. For the small vegetation plots, you're going to use that quadrat. You can also use, multiple measuring tapes. So I know some people use string, and that's a 1 meter by 1 meter in length. And you're going to sample that within that quadrat. A note here that if you're collecting samples in small plots using destructive methods, that you're going to want to set up the small plots outside of the integrated plot design or those permanent plots. However, if you're using non-destructive techniques, then it's okay to sample them within that large plot, just so you're not tampering with that permanent plot area. Next slide, please. So having set up your plot and flagged each species within that plot area, you can then begin collecting data and information. The first step is to identify each of the plant species. For shrubs and short-statured trees, having the species name will result in slightly more accurate results. But as Claire mentioned before, you can keep these higher level identifications as just, shrub and short-statured tree, and you can still get a carbon value, but it just won't be as accurate as if you were to get the specific species. Another note here that for grasses, identification can be quite difficult in a field. So sometimes they have to be taken back to the lab and identified there. And similar to the tools Claire introduced previously, the identification of a species can be accomplished with a dichotomous key using a species identification app, or ideally a local expert or a team member can help identify the plants in your area. Next slide, please. So if the species you've identified is a short-statured tree, we can estimate the carbon of that tree through a simple measurement of the stem diameter and height and using a little bit of math. So for each tree, you want to record the species name, the height of the tree, and you can obtain the height using the laser rangefinder. And you also want to measure the diameter of the stem of that tree at 30 centimeters above the ground level. So whereas the taller trees, you want to measure them at 1.3 meters, for the short-statured trees, you want to measure them at 0.3 meters above ground. And with these values, they can be converted into a measure of biomass, and from there you can use that carbon conversion factor and obtain a value of the carbon stock of that tree. Next slide, please, Emily. So if the species you identify is a shrub, we can estimate the carbon stock through taking volumetric measurements of that shrub. So this involves measuring the length, width, and height of that shrub and recording that along with the species name. There are certain regions and certain studies of specific shrub species in certain areas where they actually use the diameter of the root collar of the shrub to obtain an estimate of that biomass. And that's just where all the woody stems of that shrub kind of converge into the ground. You get the diameter of that. However, the data for that, from what I've looked into, isn't as robust, and it's species specific and regionally specific. And lastly, I'll mention here for these for smaller shrubs, around that 0.5 and lower mark, you can use what's called the clip and weigh method. And that's just where the species is directly collected and taken from the field to a lab to measure the biomass in the lab there. But yeah, that's a destructive method, and I'll get into it in a little more details in a sec. Next slide, please, Emma. So on the right here, this is an example of what a quadrat might look like. And then on the bottom, you have a little micro subplot quadrat within the 1 meter square quadrat. So within these small plots, they're gonna comprise all the vegetation under 0.5 meters. So that can include, as I mentioned before, your grasses, your flowers, your ferns, as well as your ground vegetation, such as mosses, lichens, and other types of bryophytes like that. And the first method I want to introduce for measuring carbon in these plants is called the clip and weigh method. And with this technique, all plants within a 0.25 meter square plot area are clipped at 3 centimeters above the ground and placed into sampling bags. The samples will then be brought into a lab where they'll be weighed, dried, weighed again, and that dry biomass will then be used to estimate the carbon stock of those specific plant communities. And you can see on the bottom there's just a little schematic of what that might look like in your plot area. Next slide, please, Emily. Alternatively, there are some non-destructive methods and a couple of protocols for measuring these small plots. And this is typically under the name of visual cover estimation. It's also sometimes called area-based estimation. And these techniques involve estimating the amount of cover each species occupies in that quadrat area and converting that estimate to an estimate of biomass for each of the species in the plot. So one of the visual estimation techniques that's quite popular is called the Daubenmeier cover class. And there's other, and that's a visual estimation technique where an expert is using their kind of bird's eye view line of sight to estimate the cover that each species occupies. And there's another method called the line point intercept, but it's more systematic and uses an actual tool to estimate that cover. In either case, whether using visual or more systematic techniques, the relative proportion of each of those species is converted from to an estimate of the biomass and from biomass to carbon. I will say that the caveat for these techniques, I mean, it's great that they're non-destructive, but there's no real universal method that exists for converting these cover classes to biomass. The ones that do exist are regionally specific. So typically, authors recommend that you calibrate them to a specific area by doing a visual cover estimation and clipping that area, and then using those values to then apply it to a larger area. But yeah, that's just I wanted to mention that. Next slide, please, Emily. So vegetation sampling can also be achieved in coastal ecosystems. In tidal marshes, for example, there's a strong vegetation gradient in relation to the variation in water saturation throughout the marsh. So for marshes, a common technique is to sample across this gradient or divide the area into strata to capture this variation. Along with elevation and flooding and tides, you also want to consider the time of year, as above ground biomass can vary considerably between seasons in these ecosystems. And lastly, you also might want to consider taking cores, because that's the best method to measure below ground biomass. And root systems in these ecosystems can comprise a very significant portion of the biomass in these ecosystems. Anywhere from 50 to 95% of the overall biomass is going to be below ground. So it's good to take cores and really capture that biomass as well. In seagrass ecosystems, they're submerged underwater. So a common method of capturing both the above ground and below ground biomass component is to use a large diameter core and collecting a sample. One thing to mention here is that along with these eelgrasses, there tends to be other plant materials and other life growing within the seagrass. So those can be removed as a separate carbon pool. And if you want to learn a little bit more about sampling in coastal vegetation, I think Catherine just posted a link to the Blue Carbon manual, and there's a lot more details about specific to blue carbon and coastal ecosystems in that guide as well. Next slide, please, Emily. So having gone into the fields and taken surveys of the different plots and obtained the different data and the samples, how do you actually estimate a carbon stock? So firstly, for all the methods, you want to first estimate biomass. And you want to do that using these allometric equations, which Claire alluded to and described in detail previously. And all they are simply, the relationship between the measurements we made and the biomass of the type of plant species that we're interested in. This can include species names, and maybe it's just a different category of species, and the volumetric measurements, or those diameter measurements, or those aerial cover estimation measurements that we covered. An example that I show here is that shrub biomass can be obtained by multiplying the length, width, and height that you obtained in the field to estimate the volume of that shrub. And then you take that value, multiply it by a coefficient specific to that shrub species, multiply it by another value, and that'll give you the shrub biomass for that one specific plant. And then similarly to with trees, we're going to use that same carbon conversion factor of 0.5, and you're going to multiply biomass by 0.5 to get that shrub carbon value for that one single plant. Next slide, please, Emily. So for the clip and weigh method, you're not estimating that the carbon through these allometric equations. You're actually measuring the biomass directly in the lab. So when you remove the plants from the ecosystem, bring them into a lab, they're going to be weighed, dried in a drying oven. Typically, drying takes around 72 hours at 60 degrees Celsius just to get all the moisture out of the plant. Then you're going to re-weigh them to obtain a measure of dry biomass weight. And then that biomass weight is going to be used to convert to an estimate of carbon using that carbon conversion factor is 0.5. So that's a more direct method to obtain the carbon, for typically only used for those smaller vegetation samples where you can actually clip and store it in a bag. Yeah. So here's an example of what that might look like in a lab oven on the right here. So thank you, Emily. Next slide, please. So whether you obtained a carbon estimate for vegetation using one of the destructive or the non-destructive methods, the methods for scaling up these values are the same across different plots. Firstly, you want to add up the carbon for each plant that you measured within that plot in its respective plot, and you want to make sure that you understand the size of the plot you're using. So if you used a 16 meter squared plot, or if you use the 1 meter square plot or the 100 meter square plot, you want to make sure that you get all the species within that specific plot size, and then you want to divide it by that specific plot size within that area. Next slide, please, Emily. Within each of the sites, you're going to add up the average carbon stock you calculated for each of those plots, and you can do this for small plots and medium plots at the same time, because now you have the average carbon stock, and they're all going to be in the same unit because you've controlled for that unit area. So you're going to add up the carbon stock you calculated for each of the sites, and you're going to divide it by the total number of plots you obtained, and that's going to give you an average site level carbon stock. Lastly, if you want to scale up further and obtain a total carbon stock and an average carbon stock of your study area, you're going to add up the averages of your study sites and divide it by the sum of the sizes of your study sites to get an average, and then you multiply that by the area of your study area, and that's how you get the total carbon stock of the study area. Next slide, please, Emily. To learn a little bit more or dive a little bit more into these methods, please see the Carbon Measurement Learning Library that Catherine posted into the chat. It's also going to be available here, as well as that Quantifying Coastal Blue Carbon for those interested in looking more into those coastal ecosystem vegetation sampling guides. And lastly, I just wanted to provide an example of a couple other examples of measuring those small and medium vegetation guides that are specific to either a certain ecosystem or a certain region or a specific plant type. Because with trees, they tend to be Canada-wide, but with vegetation, these studies tend to be regionally specific. So it's good. Maybe there just happens to be a study that already did all the hard work of clipping and finding these allometric equations for you, so you can just directly take that information from there. Next slide, please, Emily. So the last thing I want to do is spend about 10 minutes and go over some of these practical tools regarding calculating carbon and implementing a random sampling design. I'm going to share my screen real quick and just show these tools in a more practical sense. Okay. I hope you can all see my screen. So this is just, I just wanted to show the carbon measurement learning library, which you can find on that link. And if you scroll to the bottom, here you'll find the guides for both trees and non-trees vegetation. You can download the PDF. But if you scroll to the bottom, there's a couple other resources, a couple of these tools that you can use to help you kind of calculate the data. The one of them is the carbon calculator for forest data. And I'm just going to click on it here. And when you click on it, you'll download an Excel document. And what it contains is a data sheet. And what this does is that if you want to insert the type of tree that was measured, and maybe you don't have the tree, you just have, maybe it was a conifer species or deciduous or all, you can select the type of tree. You can input the diameter at breast height, whatever that might be. Maybe it was 10 centimeters, maybe it was 30 centimeters. You want to input it here, and then as well as the tree height. Now, tree height is an optional measurement as well, but you will get a more accurate estimate if you do have tree height. So if you don't have it, it'll still calculate a carbon stock for you, but it just won't be as statistically accurate. But here I'm just going to pretend that the height was 3 meters for this tree. And what it does is it automatically outputs the above ground biomass, the below ground biomass, the total biomass, as well as the total carbon stock for that one specific tree that you measured. And in a plot, you may have anywhere from 20 to 200 trees. So you can just go down this list, enter in all the tree data, and it'll automatically calculate that carbon stock for you, which is super handy because doing it manually, equation by equation, will be quite tedious. So this is just a great resource that I like to use personally, that we've provided open source for everyone to use. Now, I hope you guys can still see my screen. The second thing I wanted to show was that sometimes I found it quite difficult to just do something as simple as implement a sampling design, which is just, where am I going to sample? How many samples should I take? So we've tried to devise a little bit of like a decision support tool. It's supposed to be used as a guide, but definitely just provide, a little bit of guidance in how that might work. So from the first webinar that we did, we introduced the desktop analysis, which went through the Google Earth Engine kind of page, and we showed how to draw a shapefile. So I have one preloaded up here. But with this script, you're going to click run, and it's going to take a little bit to load, but I preloaded this one here. So it's the exact same shapefile or drawn area and this. And then what's going to happen is this panel is going to pop up on the right here, and it's going to ask whether you drew a study area or uploaded a shapefile. So I drew the study area. It's going to give you the option to calculate statistics. And all that does is it's going to output these statistics here, which is the study area size, the mean soil, mean forest carbon stock, as well as the total forest and total soil carbon stock. And these are from the McMaster WWF-Canada carbon maps. And that's great just to have as prior information. And then in step 3, it's going to ask if you want to determine an appropriate sample size based on 3 factors. The first is the size of the study area that you drew. The second is your desired accuracy. So what's an acceptable range of area you're allowed to be in. Maybe it's okay if you're within 80% of the true value of the carbon stock in that region. Maybe for some protocols, I know MRV protocols prefer to be within, a minimum of 10% range. And then more academic work is up towards that 5% range. You can simply just adjust that here. I'm going to keep it at 20 just as a default value. And then the second value is just going to ask you, okay, what's the probability that I'm actually within that range? So here I'm going to keep it as a default, which is, okay, I want to be 80% confident that I'm within that range. So I'm willing to accept, a 20% error in that range. And I'm simply going to select calculate sample plot allocation. And based on the desired accuracy, the study size area, and that precision, it's going to estimate a recommended sample size. So for here, the recommended sample size was around 12. So I can enter that into this box here. And it's automatically just going to randomly distribute 12 sample points within that study area for me to go take samples in. The last step, step 4, was after you've submitted this, it's going to give you the option to export these locations. So you can click export locations, and you can scroll down to tasks. And if you click run, it'll allow you to export them in multiple formats. So here you can do GeoJSON, KML, or in shapefile. I'm using Google Earth because I want to use Google Earth in the field and to actually locate my sites. I'm simply going to select KMZ. I'm going to select the folder in my Google Drive that I want it located to, and I'm going to change the name to sample plot location March 5th. I'm just going to click run. Now, this might take a couple minutes to load, but I preloaded some. This is what it might look like when it comes in. It's just a file with a KMZ format, and I can drag and drop that directly into my Google Earth. So when I select the file, it'll give me the sample point locations of those randomly sampled areas automatically. And I can click it and I can get its location. I can save this as a project and go on my phone in the field and find these locations. But like I said, it's a decision support tool. This isn't meant to be, you must sample here, it's the only location. It's just supposed to help guide you to, okay, what would a randomly sampled distribution look like? And then you can make that some informed decisions from there. So I'm going to stop sharing my screen. And Emily, yeah. Perfect. If you don't mind going to the next slide, I'll pass it on back to you. Thank you.
Great, thank you, everybody. So I noticed that we've got a couple of questions that have come in, so I will go to those now. And if you've been hanging on to any questions, now's a great time to pop them into the chat. So one of them I did answer live. The question was, is there another WWF online library that covers key information of tree species and to calculate the carbon content for Asia and Africa? So unfortunately, our resources that we've developed are just for Canada, and I am unaware of other WWF offices in Asia or Africa having a similar online library type of program. However, I'm sure that information is out there, so I'm wondering if other folks who are participating might know of good resources and could share them in the chat. I don't, if our team has anything else to add, please go ahead and unmute, but I think the short answer is here, we don't have those, unfortunately. And then there's another question that just came in from Maxime asking if the resources are available in French. So that is also something we are actively working on, getting the resources translated. I don't believe we have the carbon calculator forest data yet available. Cal or Claire, correct me if I'm wrong, but I believe that one is still to come. So please stay tuned for the translated versions of our materials. We are slow to get those done. So let's see. I don't see any other questions that have come in. There is some praise here from folks saying they love the spreadsheet, so that's great to see. Great to see that people are appreciating the resources that we've created. No other open questions. So I think on that note, we'll move along. Again, if you have any other questions that come in after the fact, our team is always available. So please feel free to reach out to us, and we'll share again that contact for us, so you can reach out there. We have another our last webinar coming up on March 26th. We're going to be talking about drones and ROVs, and we'll be joined by our friends and collaborators at Kurotu Technologies. They're going to help us to present on drones and ROVs for environmental monitoring. We also have an upcoming Carbon Community of Practice call. So many of you are involved in the Carbon Community of Practice, but for those who aren't, if you're interested in joining, we'd love to have you join the Carbon Community of Practice, again, where we get together with folks across the country who are actively measuring and monitoring measuring carbon. We'll be meeting on April 23rd. So we do have a date selected for that. It's April 23rd. It will be covering wildfire and carbon. So I invite all of you to join us for that. If you are in the Carbon Community of Practice, I will send out the invite for that shortly. And again, as Claire has mentioned, if you are interested in discussing opportunities for in-field training or any other opportunities where you'd like to collaborate with WWF, please do reach out to us. And I'm just checking the chat. Looks like, again, no other questions have come in. Thanks to Catherine for sharing the link there. And again, just wanted to share this email address one final time. If you've got any questions or comments, please feel free to reach out to us. And if there's no further questions or comments, we'll wrap up. So thanks again to all of you for joining us today. And I hope to see you again for our fourth and final webinar coming up later this month. All right, thanks everybody, and thanks to our presenters today.